Howdy, I'm Greg Hill, and this is the Phoenix Perlmongers meeting. I'm going to learn about Perl profiling and performance. What you don't know can hurt you. So, quick, just in case people don't know, what is profiling? Wikipedia and software engineering profiling is a form of dynamic program analysis that measures, for example, space or time complexity of a program, the usage of particular instructions, or frequency and duration of function calls. The most common use of profiling information is to aid program optimization. Profiling is achieved by instrumenting either the program source code or its binary executable form using a tool called a profiler. So basically, it's measuring how long your program takes. So you often hear people in the computer science world talk about premature optimization. In my opinion, it's one of the most abused quotes ever because most of the people that repeat it have no idea what it means. It was more about profiling to find where your actual performance bottlenecks were rather than just blindly looking at code and saying, oh, I can make that faster, finding out what's actually important. So the full quote is actually, we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. That's usually all that people say is that little part. Yet we should not pass up our opportunities in that critical 3%. A good programmer will not be lulled into complacency by such reasoning. He will be wise to look carefully at the critical code, but only after that code has been identified. So that's where profiling comes in. So you might say, but Perl is pretty fast, especially for a dynamic language. And, you know, most of your apps, you spend most of your time in the database. That's true. So, you know, optimize for that first, reduce the number of queries you're doing, profile your queries with the database profiling tools and make them as fast as you can. But you can also be surprised at how slow Perl can be if you don't use it very well. And a lot of small optimizations can sometimes have a large net benefit. But, you know, it's all about finding the right balance, how much effort you're putting into it versus how much performance is gained and how important that performance is. So, some caveats about profiling. They'll tell you what's slow, but not why it's slow. So you kind of have to figure out the why. It's not going to do your job for you. Sometimes the output can be confusing, especially when you're not used to looking at it, because some of the numbers sometimes don't seem to make sense until you kind of get used to understanding what they mean. And it lets you measure the impact of your changes, but you still have to, kind of goes in with the first one. And it's also fairly resource intensive. When you run a program through a profile, it's quite a bit slower than when you run it normally. But good profilers try to remove themselves from the results, so any impact that they had on the performance isn't displayed in the results, even though it actually took a lot longer to execute. Well, there's pretty much 3 different standard types of profilers. Statement level profilers record each statement of code and how long it took. Subroutine level, the whole subroutine. Block level can do like a loop or a different kind of block or whatever. In Perl, there's a lot of profiling options. A lot of these kind of built on other ones. I don't know the history of all of them. Don't really care. There's quite a few. But really, the only one that you should care about is devel NYT prof. Oh, I guess I skipped ahead, sorry. But how they work with Perl is they attach to the Perl debugger. And that's DB. Sometimes if you're familiar with the debugger, you can mess with stuff within DB. And not to be confused with database, it actually means debugger. And, you know, there's much voodoo and many sacrificial chickens involved. I really have no idea how it uses the debugger, but I know it hooks into it because of how you have to invoke it with the Perl-D. That tells Perl to use a package for the debugger. And most of them gather their data in memory. When the program exits, they flush that out to a file. Sometimes they have tools to translate that file into something useful to actually look at. And devel NYT prof has, from what I've seen, the best options for display and the most options for actual profiling as well. So NYT prof, it started at the New York Times, thus NYT profiler. Tim Bunce, I guess it was started by another guy, but then he became kind of the primary guy on it because they merged their, he was working on a different one and they merged together, and then, I don't know, you can ask him the history anyway. He's the guy that wrote DBI, so he's a pretty smart guy. It's written in C, so it's as fast as possible, and tries to remove itself from the results like I mentioned earlier. But, you know, profiling is always going to affect the exact results, so you can see something it took, you know, 32.2 seconds. In reality, it might have taken like 29 seconds or something, but the before and after relative numbers are what's important, the percentage differences. It also has shiny HTML reports, which we'll see later. And it does all three of those profiling types: statement level, block level, and subroutine level. So it has a lot of good information. So the basic way you use it, you invoke it with Perl-D. Well, first you write some script.pl that does what you're trying to profile. After that, will generate an nytprof.out file, and then you run nytprof.html on your command line, which generates the HTML reports, and then you can load those in the browser. And then you figure out what's slow, fix it, redo it. Still too slow, do it again. This is kind of an iterative process like that. So now I shall try a live demo. All right, so this is a little script I wrote for purposes of demo. Is that big enough font, or do I need to increase it?
Probably make it a little bigger.
Good.
Can you make the background black, dark? I remember something about dark background being better.
Yeah, but don't worry about it.
Yeah.
Sorry. Yeah.
I don't know a quick way to do that.
Yeah, that's cool.
So anyway, I wrote a factorial function, 4 different methods, wrote a recursive form. Then I had recently read about tail call optimizations and recursion, so I said, I wonder how that will affect it. So I wrote a tail call recursive form. And then my scroll wheel isn't going to work for me. I wrote using a standard Perl for loop version where it just makes an array out of that, and then a C-style for loop version just to see. So when you run this, so here we're going to calculate the factorial of 1 million using a C-style for loop. And then, woo! So then, see the files there, nytprof.out. I think there's a -- view option, or maybe that's added in a newer version than what I have installed. Anyway, so that generated it. See, now there's this nytprof folder. It's got a bunch of HTML files. So rather than do each one separately, I'm just going to show you some of the results. Wrong one. Okay. So here's the recursive factorial version. It took 27.8 seconds to calculate the factorial for 1 million. And as you can see right at the top.
Can you make the font bigger?
Yes, I can make the font bigger. Thank you. Good. Okay. Forget about these things in advance. So most of this other stuff is just because I did use benchmark at the top for a different version, different purpose. So really all that you won't need is here. So you click on reverse fac. Since it's such a small function, it doesn't really give you a lot of useful information. It took 1.8 seconds to call shift a million times. The if int less than 1 check took 1.56 seconds to call a million times. This line was called, took a second and a half. Anyway, so this says how many times the line was executed, how long the total took. When you mouse over it, it shows you average. You like averages that are microseconds. When they get into milliseconds, it's actually means something's fairly slow. Because unless you're doing like a database call or something over the network, anything more than a millisecond is actually kind of slow, which is something you kind of figure out as you use it more.
Right.
So anyway, yeah. And then when you, some of the ones you have later, it'll have more stuff where you can click around and see. But like here it says, you know, this was called from here. So it's called from itself 999,999 times. It was called once from here where I did that. So it lets you jump around. It has links that let you jump around to between different areas, so you can kind of dig into stuff a little bit more. So just for sake of fun, the tail call version took 31.7 seconds versus what was the 27.8 seconds. So it was actually slower. I don't know why. I guess it's just because it does more, because it has to look at the values, but then it has to push them back into add underscore, and that just added up, I guess. Because it's doing it a million times. A small difference makes a big difference. Anyway, I thought that was interesting. Probably uses less memory, though. I actually accidentally invoked it. Well, didn't accidentally. I was going to do it with 10 million because I wanted it to take a bit of time, and I didn't really think about it. But the recursive form that didn't have the tail call actually started throwing errors because Perl's call stack had issues with recursing more than a million or so times. Strange that, huh?
Yeah.
So the for each version took 7 seconds, where it just generated a large array and then looped over it. And then the for C-style for loop actually only took 4 seconds.
Woo!
So go C-style for loops. Yeah. I probably could have done it with a while loop. That would have probably been about the same, but I didn't think about it till just now. So that was kind of the basics of how it works. There's not a lot in this specific example, but we'll get some more complicated examples in a minute. So I just want to talk a little bit more about some of the options you have with NYTprof. There's this NYTprof environment variable. You can tell it to start at different phases. So start equals init, waits until it's finished the compilation phase with Perl, and then only profiles your runtime performance, basically. You can start equals end, and it will basically only profile anything in an end block, which I guess could be useful. Maybe you have like some garbage collection performance issue where you've got a circular reference it can't clean up and you're trying to figure out where it is. That could help, I guess. I don't know. I've never used that actual one. Slow ops equals 0 will not profile some of the Perl opcodes. I guess it adds a lot of performance overhead to do it. I don't know exactly why. I probably should have remembered more about it when I wrote it on there. But you can also manually control when you start and stop profiling. If you do start equals no, it won't automatically start. And then in your code, you can call db enable profile, give it a path to a file name. db disable profile will pause collecting information, so then you could then enable it again later if you wanted to. And finish profile writes all the data that's in memory to your path. There's a bunch more options on Meta CPAN. But for the most part, the only options I've ever really used are the start equals init to skip compilation performance, because a lot of time that can be confusing in the results if you have a large compilation time and you really only are caring about the runtime performance. You can also do it in parallel. NYTprof will follow forks. It writes out a separate file for each PID that you fork to. And then it doesn't work with threads, though. It's not thread safe at all. I think he said you can try it or patches welcome or something, but he didn't care. I don't care either because I don't use threads with Perl. Then there's a handy utility called NYTprof merge, where you can take all of those various files that per PID and it merges all the data together and gives you the time it took total for all processes combined. You can get a lot of noise from stuff. Your actual forking code, or if you're doing wait PID, will add extraneous information to your output, so you kind of have to figure out how to ignore that and get to the stuff you're looking for. but it's invaluable for figuring out locking and condition issues in multi-process applications. That's when I used it. And there's an example I'll show of that. So here's some use cases where I've used it to find and fix some performance issues. We used to have these mix-ins that, I wrote the mix-in code in like a day, so we didn't really optimize it for performance because we just wanted mix-ins. And then later on, after we had kind of evolved our code base, we wanted to switch to roles. And the new code, we wanted to make sure it performed better than the old code because there were some problems that we had found in other profiling examples where the old code was making it slower. So I spent some time after we had finished writing the new code, doing some profiling, optimizing out some of the common cases, making it as fast as I could, and also making sure that the legacy classes that had to use some of the features that we didn't need anymore that made things faster still performed better than they did before. So behold the results. So the new objects, I wrote a profile, 100,000 calls to new. It used to take 17.3 seconds in the mix-in based code. Now it took 3.1 seconds, which was an 82% reduction, which is pretty significant. And then the legacy objects that still had to do some of the extra stuff that the new objects didn't need to went from 31.5 to 18.3 seconds. So there's a 42% reduction. They're still 6 times slower than the new ones, but still a pretty significant reduction. Then I thought, well, how does this actually impact real world code? You know, like we don't really create 100,000 objects in a single, hit to our application. At least hopefully not. Probably there are some cases, but anyway, so I took our absolutely slowest API method. Gets a list of all of our provisioning parents. There's a couple thousand of them, and for each of those, it gets a bunch of extra metadata that's related to them. So I ran that 1,000 times, and it took 401 seconds the first time. With the new code, it went down to 343 seconds, which is still pretty heavy. That's, from 400 milliseconds basically per hit to 40 milliseconds. But that's almost 60 milliseconds saved per API call just from making the object constructors faster. Imagine if we could, reduce the database load as well, but that's coming later. I had we can look at that if you guys want. I think I had it open. Do you guys want to see some of that? Okay. The API one's not that. So these are the newer objects. So the before stuff, you can kind of see the NYT prof. Is that still big enough, or does I need to make it bigger?
Looks good.
So you can see before, we're calling this clear error thing a lot, because all of our old code used the error codes to track and pass error messages around. The new codes used exceptions and didn't need that stuff, but since both the old code and the new code use the same mix-ins, it did it by default. So, obviously getting rid of that would be helpful, but you can kind of click into it. And you actually see that, no individual statement here is that huge. 1 millisecond average, or microsecond. Ooh, nanoseconds. But it just added up, I guess. It has to initialize all these class variables and a bunch of variables on the object every time it creates a new object. So that was, obvious place to start. But if you just, start with the very first thing, the constructor. And we realized at runtime it had to actually, had to add all of your mix-ins to your package. And it only did that once per package. But then if you had a subclass, that package had to do it separately, even though it should have inherited the mixins from its parent class. So one of the goals was to do it at compile time, so we could do it at compile time and also make it inheritable, so that only the top class that needed the mixin would compile it, and then all the child classes would automatically get it, which would reduce a lot of hit, but then also that it would be done before you even hit your runtime code at all. So anyway, I mean, that's kind of how you do it, and you're like, oh, wow, this took 6 seconds to call this. And then you can see over here, average is 42 microseconds, 21 microseconds. You can see my cursor on there, right? Okay, yeah. And yeah, I don't know how much, I'm not going to really dig into a lot of these that much, but just kind of went through these one by one and optimized them away until it got to performance, and then, or an acceptable performance level. And so now that same thing, you know, went down to 1 second instead of however much it was before. And interestingly enough, doing ISA checks is the second slowest thing. Something that I like to do, because sometimes this orders by exclusive time, which is how much time it actually spent in the subroutine, not including any subroutine calls it made outside of itself. But the inclusive time includes everything that it also then in turn did. So if you actually sort by inclusive time, a lot of times you can, sorry, can't point at my laptop. You can just go down until you find where there's a big jump, and then you know the one above that took a lot of time. So sometimes, you know, you've got a call stack that's several layers deep, and then you can see, oh, when it hits this part of the code, that's where a big chunk of time starts taking up. And so you can kind of focus on looking at that and what it's doing, because even though the exclusive time is important to know how much time the code actually spent in that subroutine, the inclusive time might be an indication that that subroutine could be refactored to do fewer external calls. So if you have a subroutine that's calling some other subroutine, you know, 15 times, that other subroutine combined is slow, but you can go look at it and say, oh, I only actually need to call that subroutine once, and then I can cache the results locally and reuse that variable. Then that's where inclusive time becomes useful, because it's not always obvious that you called something a lot of times from a single location when you might not have needed to. So
you sort it by inclusive time, and then you look for jumps in the exclusive time? That's what you're saying?
no, I look for jumps in the inclusive time. Yeah. I think this might be more obvious when we look at the parallel one, because the inclusive time on like the fork code is like huge, but then it includes all of the time waiting for the children processes to return. And okay. So case number 2 was some rate limiting code that we wrote. The first iteration was written by someone else, and it was taking about 80 milliseconds per hit, which is unusably slow. I mean, Google gets mad if they take more than like 10 milliseconds to return their search results. And this was just the rate limiting portion of the API. It was taking 80 milliseconds per hit. So, you know, forced rate limiting through slow code is kind of funny, but not really. Because, yeah, kind of makes it pointless. Just for a point of reference, DB queries with good indexes are usually like 3 to 10 milliseconds, depending on the complexity of the query. So 80 milliseconds is the equivalent of like 15 to 20, or no, sorry, 20 to, I can't add, 8 to 20 deep database queries, which is a lot. So I spent some time working on it, had to rewrite a good chunk of it, got it down to about 8 milliseconds was what it was showing in NYT-prof from 80. And I also fixed some problems with it. It wasn't limiting correctly, and if your activity died down and then came back up, it wasn't figuring that out right. And I also added some locking to it so that if multiple processes wouldn't stomp on each other. And it was still a little bit slower than we wanted. We didn't really want 8 milliseconds just for rate limiting, but it was fast enough, so we called it good. And then funnily enough, I actually don't have the NYT prof output from the original one still. Rate limiting came up again. So this time, that nice locking code that I wrote in the previous iteration, turns out if you get a DDoS and your API doing API requests to show prices for your products on your website, then eventually all of those API processes were all waiting for locks. So the API quit responding to requests because every single process that was available to process a request was waiting to get a lock and fighting over it. So we again pulled it in the profiler. This is where I used the NYT prof merge stuff because we needed it in a case where there was a bunch of processes contending over a resource. We retweaked the algorithm to use atomic methods so that didn't need to have any sort of locking, and it actually ended up, some other changes that we discovered while we were doing that made it end up being actually faster than it was before and completely removing the potential for condition. And I'm going to show what that looks like. So I actually ran the rate limiting code in 2 different ways. I did one where it did 160 processes and each process did 200 rate limiting. Well, did 400 rate limiting increments. And then I also did one where it just did one process and did, I think it was 200,000 rate limiting things in sequence, just to make sure the performance on that, because that was all we had measured before was the serial performance. I wanted to make sure that we were still meeting our baseline for that. So these will be some fun numbers. So you can see here, generated a separate file for every PID. But then when you look at the results, they become kind of interesting. So you have this. It spent 6,000 seconds calling read. That doesn't really help a lot. Like, that's in a CPAN library that's actually used by the HTTPS portion of LWP request, which I had to figure out. And then, but so that was weird. You know, why is it spending that much time calling that? And then here is like, oh, sleep. What the heck? Still not very useful. And then, you know, cache mem, cache dfast, add. Okay, we're calling that a lot, I guess. But then, so as you're looking at the exclusive time, you know, you get down here, and it's the actual first method that's, oh, here's the sleep thing that was waiting for the PIDs. So it's got an extra 78 seconds waiting for all of the processes to finish. But anyway, the first place that you actually see anything that is actually related to what we're doing, the LW rate limit increment thing, it only took 57 seconds compared to 6,183 here. So that doesn't seem that bad when you look at it. You're like, but if you look at the inclusive time, it includes all of that. So it was actually what it was doing. And so that was kind of where, if I can get, by the way, Macs are the only people who figured out how to do a touchpad.
Yeah.
So this is where it came interesting to do the inclusive time. So it's like, oh, slow, slow, and then there's a big jump from increment to there. And so it's like, oh, okay, so I'm spending actually a lot of time in increment itself because the next one was a huge jump down.
Okay. I get what you're saying about that now.
So you dig into increment, and it's like, oh, this memcache locking thing. Well, that's weird. That shouldn't take 76 milliseconds per hit because a memcache lock is like double-digit microseconds usually. So I clicked into there, and then it's like, huh. apparently failed to add a bunch of times because all the processes were calling add. Add's an atomic method in memcache that if it gives you a value back, it means that you were the first one to create that key. And if not, it gives you undef back, so then you know somebody else has the lock. I guess I should have explained how the locking works with memcache. Basically, you try to create the key. If it already exists, that means someone else has the lock. So then you sleep for a tiny amount of time and retry, because hopefully they've let go of the lock by that. And so then I was like, oh, I spent almost 3,000 seconds calling time high-res sleep. So that's where that came from, that one that we saw on the first page. So obviously that's the problem. So we went in and we fixed it. We just basically rewrote the algorithm not to require any locking, and that got rid of all that. Made some other tweaks as well. I'm not going to go into all of them. And then if you look at the after one, still got all the PID files for every... Come on, I'm using 2 fingers here. So now it's, much smaller numbers. 311 seconds versus the, what was it, like 15,000 or 18,000 on the old version. And the numbers aren't exactly right because it has all the extra time that it spent waiting for the child processes to finish. But much better. And yeah, since this has happened, we haven't had any issues. Even when we get a DDoS, the API stays up. So yeah, and so now, the first result is actually our code. It's not something in some C-plane library that we did. So I'm not going to really go through the algorithm, but just to say that these multi methods on memcache are pretty sweet. Get multi, add multi, set multi, because it does all the different servers in parallel that you need to hit if you're doing multiple keys. And it also only sends one request to each server, so you avoid all the network overhead for each individual call. Anyway, so back to reality. So that was that one. So startup time, this was an interesting one. Our API is really slow to restart. We noticed this a couple of years ago, and it's actually gotten worse because we've converted more, well, I don't want to give away the punchline, but anyway, it was really slow because it takes forever to recompile all of our code. And, who cares about compilation time? Turns out pretty much everyone should, because what happened was we use fast CGI because we haven't been able to update to PSGI yet. But we have a process manager that runs as a daemon. It listens on a socket that Apache writes all the requests to, processes the request, returns it. So during the time that it was recompiling the code, any requests that came in would basically they would time out. The FCGI would never pick them up. Apache would finally time out. And so we had a lot of errors every time we had to push code out and restart the API. We had this 13-second window that we couldn't serve any requests, which doesn't seem like a lot, but it's stupid. So we kind of made this hack on the process manager that it's extremely hacky. I'm not very proud of it, but it fixed the problem. It takes all you do a graceful reload, it takes all the current children PIDs, throws them into a file, detaches them all from the current process and makes them zombie processes, and reloads itself. When it gets to that point in the code again, when it's done compiling, says, do I have any PIDs in this file? Okay, I'll kill all those off while I spawn my own new children to process the new incoming requests. And there's actually still a little window there where we occasionally get an error, but severely reduced. And the big thing was, after we did the profiling, it turned out the problem isn't our code. Our code doesn't really spend that much time compiling. There are some places we could improve it. I thought it was maybe where it was building all of the API method paths. We have this dispatch object that translates the URLs into function calls, basically, that has to know which API methods are available, and it has to do this recursive structure. And so I thought, okay, that's probably what's slow. And it turns out that wasn't that slow. That was less than a second of the 13 seconds. So, and then this was the kicker. Upgrading from Perl 5.8 to 5.14 went from 13.3 seconds down to 4.2. That was it. No other changes, just upgraded Perl and all the CPAN modules, but that actually wasn't the problem. It was Perl itself. So it's, yeah, seriously, what the heck? So here's something you get to learn about. Diamond inheritance. So when you have, it's called diamond, I'll explain it after anyway. So I made this little example. You've got packaged mammal, it knows how to eat. Horse is a mammal, donkey is a mammal, it also knows how to eat differently. A mule is a horse and a donkey. When you call the mule's method eat, which version does it use? Does it use the donkey version or the mammal version? Because, you know, it inherits from both horse and donkey, so you would think it's going to do donkey because donkey should override mammal. But the problem is the way Perl works is it goes depth first when it does inheritance. So it goes mule, then horse, then mammal, then donkey, then mammal when you have diamond inheritance, which is what, I guess I should have moved donkey over here so you could see the diamond pattern. You got a child that inherits from two classes which both inherit from the same common ancestor. So you think, oh, well, this is a really stupid way to design code. If I ran into this, I should probably think of a different way to go about it. But not everyone thinks that way. So there's this thing called class C3. And what it does is it fixes that method resolution order so that it would go mule, horse, donkey, mammal, which is what you would expect. And it does all of its hooks at compile time to figure out all the method resolution order for every class that uses it. It's ridiculously slow. Not just at compile time, it actually has a pretty good runtime performance hit too. So there's this XS version. That's a lot faster, right? We were actually already using the XS version. So that, 9 seconds that we saved was not alleviated at all by XS. And, this should have been assigned to not use diamond inheritance, but Dybix class. For some reason, Dybix class uses diamond inheritance. And instead of seeing that as a problem, they use class C3. So it does actually try to use the fastest method it can. So if you have the XS version, it'll use that, 5.8. But then in 5.10, largely due to Dybix class needing class C3, they added an MRO pragma, which is method resolution order. So you can tell it to use the depth first one. And so if you have 5.10 or above, it uses that. It's actually quite a bit faster, obviously. It went from 13 down to 4. But it's still not, it still adds a pretty significant chunk. If it didn't use this at all, I would think that 4 would go down to more like 2 to 3. And so a better solution, they would have used some kind of roles system or something to do method, not inheritance, composition, class composition. It's rather than using multiple inheritance. So I used to always think when people said multiple inheritance is evil, that, oh, you just don't know how to use it right, or being pedantic. But turns out multiple inheritance is kind of evil. I don't think I'll ever use it again. Yeah. Oh, I skipped ahead. I actually can show. So yeah, this is fun. You're gonna love this. So you'll notice that it's full 5 methods down. This is just compilation. All it did was compile our API server and then exit. That's all it did. Spent 3.5 seconds calculating method dispatch table in the XS version. 1 second applying the method dispatch table. And then almost a full second in the wait, what? It's plural.
Versus non-plural.
I think this loops through and then calls that. And then cleaning up after itself, it spends almost another full second. Now, granted, we have a lot of database tables, and they all have DivX class schema objects. So we have, yeah, I mean, it's a lot of classes that it's compiling, but holy crap. So the dispatch tree that I thought, you know, oh, this is probably where it's slow. Yeah, it was actually only 600 milliseconds. And then this is also DivX class stuff. And then this is DivX class stuff. And this is where we actually get to actual DivX class register source, is where all this other crap gets called from. Oh, and more class C3 stuff. Yeah. So the it's actually kind of fun. The 5.14 version. It's like we could actually, you know, look at optimizing our own code now, because wait, the first thing that's actually is loading our MIB files for our SNMP libraries. Oh, well, you know, that's something we could optimize. But notice how these are not multi-second numbers. They're all low milliseconds. Quite a bit different. And the only thing in class C3 that gets called is that it calls this and it says, oh, you have MRO, I don't need to do anything. I mean, that's... So that was kind of insane.
Yeah.
So that was that. And yeah, so we had no idea that DivX class was just a huge performance problem until we profiled it. And then I don't mean to knock on the DivX class guys. I mean, DivX class is pretty great for a lot of things. It just surprised me. And then some other useful tools. Benchmark, if you just want to do direct comparisons of multiple algorithms, it's a lot better because it doesn't have all the overhead of profiling. It just gives you comparison numbers. I'll actually show you an example in a second. And then, you know, if you, for some reason, you can't attach a profiler to your code, you can always just pull out time high res and get fractional seconds. I forget, it goes down to the nanosecond, I think. So you can just do before and after, you know. This was the time before, this was the time after. The difference is this many milliseconds or nanoseconds or whatever, and then throw it in a log or spit it out to standard error or something. And yeah, I'll do the benchmark. See, I think if you pass no parameters, it does the benchmark version. Probably should have set up a window with this beforehand, sorry. I went down a folder. This actually takes a couple seconds because it's doing, it's calculating the factorial of 1,000 times for each of the 4 methods. Anyway, but this is, I don't have anything else, so we'll just wait for it. Just so you can see the, that's actually kind of small too, huh? Wonder if Control Plus works in, of course not. It's putty, so I have no idea. Yeah, I should really reformat this. It does finish, I ran it before. But I am doing a live demo, so, you know, anything that can go wrong. But it's just, I just want to show the output's kind of interesting on the benchmark comparison stuff. Oh, I can actually show you the code. So yeah, here's the benchmark code. It just calls it with, or doing a factorial of 10,000 1,000 times, sorry. So then you could just comp these, how many times you want it to run each method. And then your keys are just descriptors. So I just use these keys, the same recurse tail for each in C4. And then your values are subroutine reference that it calls each of them 1,000 times. Tallies all the results and gives you comparisons. So here you go. So I don't know if you can read it, but the tail call did 30.2 times per second, which, and then, you know, 49.2 for the recursive form. So this is actually interesting that it changed. Doing a smaller factorial, but doing it more times, it actually was faster to do the tail call. Wow. And that I thought was interesting. It also At one point, one of the things I did, the for each was actually faster than the C4, but I guess this wasn't the example. Or no, it is, yeah. So the C-style for loop is 347 per second, but the for each is 422, which is really interesting. I don't know why. I didn't dig into it. Yeah. So it's a smaller number of iterations per thing for some reason. I mean, I guess the overhead with the for each probably was initializing the array that was 1 million elements long.
Right.
So that adding all that memory probably is what made it slower with that example.
Yeah.
But then anyway, it gives you comparisons. So this was 1297% faster than tail call, 757% faster than in the recursive. So you can kind of just get a table. And it almost just seems backwards at first.
Yeah.
Because you got to learn how to read it. I've read it backwards before and switched to something that was actually slower and then found. So make sure you actually look at these numbers first and say, okay, this is obviously the fastest because it did the most per second.
Right.
Anyway, so that's how benchmark works. And that's it. Any questions? Did I manage to take more than 20 minutes this time?
Yeah, 46. Actually, I don't have a question, but I just thought I would share a surprising thing that NYT prof showed me one time with some of my own code at home. I was just, curious to see where it was slow. Of course, I'm thinking I've got a loop that has a regular expression that just keeps parsing through, and every time it finds a new tag, it processes that, and then it keeps going from that point on. So I'm kind of thinking, because I'm looping so much, that might be where I have some slowness. Turns out the slowest piece of code was that I was using overload, and I had objects that were getting stringified when they didn't need to be. All I had to do was go in and clean up a bunch of those where it didn't really need to be stringified, and it was being stringified. And it turns out that the regular expression loop was blazingly fast. So.
Yeah, it's actually pretty amazing how fast regular expressions are.
Yeah.
You're like, oh, 2 microseconds. Yeah, I can live with that.
Yeah. So that's cool.
Cool.
Yeah, one thing I've liked messing with MIT prof is if I'm running it on code that I haven't read a lot of the code, the source code. You can almost run NYT prof on it,
yeah, it gives you
it's spending a lot of its time, and then go check that out and click around, and then
you dig through the code, and you're like, oh, that's how that works.
Yeah, this must be important. It's taking a while.
Yeah,
just see what's going on in there, so that can be kind of fun.
Yeah, it's interesting. Sometimes it's fun just to profile random things, and they're like, oh, I can make that a little bit faster.
Yeah.
Yeah. Luckily, if you're done it as long as me, you kind of forget whether you're the one who actually wrote it or not after a while. I might have written that.
Yeah.
Anyway, that's it.
Cool.